Welcome. I welcome you all on Physics Addhyan. And in the previous lectures, we have studied about the matrices and their properties, basic properties of the matrices, and different types of matrices we have learned and their properties, and we did a few problems there. So in this lecture, we are basically going to deal with diagonalization of a matrix. What are the necessary and sufficient conditions for it? And then we will move on at some properties and how to diagonalize a matrix and what does I mean by diagonalization. What can you do if you have a diagonalized matrix? So till now we have studied that much, and now we are going to study this. So let's start with it. Basically, I have changed the theme from white to black, so it seems me a very cool way to write on a blackboard and with a different color, so it's good. So let's get started. The diagonalization of a matrix. So suppose A is a matrix. You have a matrix that is A, that is an n cross n matrix. Let's say its eigenvalues are lambda 1, lambda 2, lambda 3, such that it is an n cross n matrix, so it has n eigenvalues. These are the eigenvalues of this matrix. So each eigenvalue will correspond each eigenvalue will correspond an eigenvector. Let's say corresponding to x1 lambda 1, it is x1, corresponding to lambda 2, it is x2, this is x3, and such that we have n eigenvectors. So these are your eigenvectors of a matrix. So there was a matrix A, you know its eigenvalues, you know its eigenvectors. So there is a condition: if all the eigenvectors if all the eigenvectors of a given matrix, sorry for this because I am having a cough little bit. So given matrix A are, if all the eigenvectors of a given matrix A are linearly independent. So linearly independent means all are independent of each other. I mean there is no dependence of xi's at any of the eigenvector. So if all the eigenvectors of a given matrix A are linearly independent, then the matrix is not is can be diagonalized. Then the matrix can be diagonalized. So this is a necessary condition for a matrix that has to be diagonalized. So all the matrices that are square cannot be diagonalized. They can be diagonalized only if they have these types of independent eigenvectors. So if you have independent eigenvectors, then what you can do, you can define a matrix P in such a way that this matrix P, so you have n eigenvectors, so there you put this eigenvector as x1, another column as x2, and such that you put the n eigenvectors in this matrix. So this will be an n cross n matrix. So define a matrix P in such a way that these are the columns of this matrix P are the eigenvectors of the matrix A. If this is such, this is an n cross n matrix, then you can find out its inverse also. P is equal to what? So you can find out easily by just doing some calculations. You can find out the inverse. So till now we have defined a matrix A, its eigenvalues, its independent eigenvectors that are linearly independent. Then the matrix can be diagonalized, and we define a matrix P in such a way that its columns are the independent eigenvectors of matrix P. Then we find the matrix P inverse. Then we again define a matrix that is dA. This is P inverse AP. We write this matrix P inverse here, this matrix P here, sorry, this matrix P here, and this was your original matrix A. If you do such a type of transformation, that is P inverse of AP, P inverse is the P is your matrix that is defined by the uh, whose columns are the linearly independent eigenvectors of that matrix. P inverse is the inverse of that matrix, and A is your matrix. If you find dA, that is P inverse of AP, the very important property or what you see in DA matrix that have only diagonal elements, it does not have any of the cross elements like x1 and that is 0. It has only a1, a11, a22, a33. These types of elements will be present in that matrix DA. All other elements will be 0. So this type of transformation is called the diagonalization of a matrix. So diagonalization is nothing but a transformation of a matrix. Now one can ask a very simple question: why? Why only the independent eigenvectors? Why not independent? What happens when there is linear dependence in eigenvectors? So let's see what happens there. So let's ask here a question. And so the basic question was, what happens when there is a linear dependence? Let's say x2, that is the second eigenvector, has a dependence on x1 by any scalar, let's say that is m. x2 is m times of x1. So that is eigenvectors are linearly dependent. If this happens, then what is the case? If that happens, then if two of any of the columns of a matrix are equal, then you know the matrix which you defined as P, its determinant, when will you find its determinant of P will be 0. So if the determinant of that will be 0, it means that P inverse does not even exist. If P inverse does not exist, then you cannot diagonalize a matrix. This implies that A is your matrix. A cannot be diagonalized. So that the existence of P inverse is necessary for diagonalization. That is the reason why the eigenvector should be linearly independent. So let's see what our matrix or how our matrix will look like if that is diagonal. So if we do the following transformation, the transformation which I have just derived, that was dA is nothing but P inverse of AP. If you this type of diagonalization where dA is the diagonal matrix corresponding to that is A is your matrix. So dA is a diagonal matrix that corresponds to A. If you wish to write the matrix form, then dA will look like this. Like you have an n cross n matrix. Sorry for this. You have an n cross n matrix. So whose diagonal elements are the eigenvalues lambda 1, lambda 2, lambda 3, and such that you can reach up to lambda n, and all the other terms are 0 here till this n. All these columns are, all this block is 0, all the upper blocks are 0, only the term which exists is the diagonal. So that is the diagonal matrix of DA. So if you can claim that all the eigenvectors are independent to each other by your inspection, then you can directly write the diagonal matrix, that is just your eigenvalues of the matrix. So that was about the transformation of a matrix. So this is basically diagonalization is nothing but it is an application of transformation of a matrices. So like all other transformation, this diagonalization is one of the transformation where you need P and P inverse in such a way that dA is your diagonal matrix. So P in that seems that P is the matrix that is formed by the independent eigenvectors as a column of that matrix. Okay, so that was about the diagonal transformation. Let's move further. Okay, let's ask one more question. Can you comment on the diagonalization of a matrix by seeing its eigenvalues? Because you can get eigenvectors by the eigenvalues. So let's make one more comment on this. So let me move down. Okay, so here I am making one more comment. So this is if all eigenvalues of the given matrix are non-degenerate. I will explain what I mean by this. Non-degenerate, then corresponding eigenvectors will be always that is linearly independent. So the claim is that if the eigenvalues of a matrix are non-degenerate, then the corresponding eigenvectors will be always linearly independent. What we want the linear independent eigenvectors. So what I mean by non-degenerate, suppose there is a matrix A. Let's, for simplicity, let it call as 3 cross 3 square matrix. Let's say its eigenvalues are lambda 1, lambda 2 and lambda 3. Let's say, for example, let's choose lambda 1 is equal to 0, lambda 2 is equal to 0, lambda 3 is equal to 1. So you can see that two of the eigenvalues are equal. So we can say there is a degeneracy of eigenvalue that is 0 of order that is 2. So we have an eigenvalue of a matrix A, that eigenvalue is 0 and its orders is 2. So if there are degenerate eigenvalues of a matrix, then you cannot comment upon anything of the linearly independence of eigenvectors. Okay, so if there is non-degeneracy, it means lambda 1 is not equal to lambda 2 is not equal to lambda 3, then this implies always linearly independence of eigenvectors. But remember, the very most thing which I wish to emphasize here, if there is a degeneracy of the eigenvalues, let's say here lambda 1 is equal to lambda 2 is not equal to lambda 3. So there are like this such case, there is a degeneracy of order 2 of the eigenvalue that is 0, then the eigenvectors can be linearly independent, can be linearly independent, or can be linearly dependent. They can be. Then you have to check it. If eigenvalues all are unequal, that is non-degenerate case, then you can surely say that all the eigenvectors are going to be linearly independent. But if eigenvalues are degenerate, then you have to check the eigenvectors whether they are linearly independent or not. Because in case of degeneracy, there is no such any theorem or any such statement which says that says about the eigenvectors, that the dependence of eigenvectors. Okay, so that was about the how we can claim about the eigenvectors are linearly independent or not of an eigen by seeing the eigenvalue. Let's move further. Okay, so let me write this what I have just stated about the second part. It was if the eigenvalue of given matrix are degenerate, that what I said are degenerate, then the corresponding eigenvector will be either linearly dependent or linearly independent. That's what I mean, that you have to check. You have to check that statement whether they are linearly dependent or linearly independent. So quickly, let's see an example of diagonalization. So let's do a very 2 cross 2, very starting from very simple. Let's say there is a matrix A. Let's The elements are 5 4 1 2. Let's, for simplicity, just to understand the basic notation, and you can easily find that this eigenvalues are lambda 1 is equal to 1, and let's say lambda 2 is equal to c. Not say, when you will find, you will get this. Okay, let's do a quick how to get this. Lambda 1 plus lambda 2, that is trace of a, that is 5 to 7. Okay, the product of the eigenvalues will be determinant of A. If you find the determinant, that is nothing but 10 minus 414, that is 6. So you can just substitute, you can solve these two equations and you will get this. Okay. Then if I write the characteristic equation, then the characteristic equation is Ax is equal to lambda times x. Lambda is the eigenvalue. Then A minus I times lambda times x is equal to 0. If you find this, you will get, or you can find this way also. This is 5 minus x 4 1, that is 2 minus x. Let x be the eigenvalue, or you can put here lambda. Let me put it here lambda. Let me put it here lambda. That time its determinant is equal to 0. Then also you will get the same result. So you can see that these are linearly, so not these lambda 1 and lambda 2 are non-degenerate, so you can directly claim that dA will be its eigenvalues 1 0 0 6. Okay, so now your task is to verify this by doing P inverse of AP, where P is the eigenvector corresponds to this lambda 1. So this is x1, this is x6, and then you find the P inverse and do this, you will get the same result. So I emphasize you to do this because this is a very simple 2 cross 2 problem, and it will help you to do the mathematical tricks that you will be required to find the P and P inverse. So it will be easy. It will be get only 2 or 3 minutes to do that. So please do that. Let's move on another example. Okay, so let's move on another example, that is example number 2. So let's the matrix be A, that is your very simple 1 1 1 1 1 1 1 1 1. So that is your matrix. So if I say you to find the eigenvalues, you will simply calculate this by the eigenvalues are 0 0 and lambda 2 is equal to 3. So there is one quick way to find this. I have told you that if any of the column or any of the row is a multiple of any of the column or any of the row, then all the eigenvalues are 0 except 1, that is the trace of A. Okay, so that are the eigenvalues. So you have the eigenvalues. So see, these are linearly dependent eigenvalues. So sorry, not linearly dependent. These are degenerate eigenvalues. I'm very sorry for that. So these are degenerate eigenvalues. So this is the part of the second part where I said that there are degenerate eigenvalues. Then you cannot comment anything about the eigenvectors. It can be linearly dependent or it can be linearly independent. So let's see what is here. I am not going to do the whole calculation because I have told you all these things how you can calculate. So something is left for you, that is this mathematical calculation. If you do, then you will find that with respect to lambda is equal to 3, there will be one eigenvector, and for lambda is equal to 0, there will be two eigenvectors. So when you transform that, when you will ax is equal to lambda x for lambda is equal to 0, you will get that all the eigenvectors, that is x1 plus x2 plus x3 is equal to 0. This x1, x2, x3 is a eigenvector. So for this condition, you can claim there are two eigenvectors for, let's say, x1 is equal to k, x2 is equal to minus k, and x3 is equal to 0. For this, you will get an eigenvector that, let's say, that is x1. So in normalized form, it will be 1 by under root 2 minus 1 by under root 2 and 0. So there, this you can be the first eigenvector. For second, you can put this x is equal to k, x2 is equal to k, and x3 is equal to minus 2k. This also satisfies this equation. So for this, if you wish to find the normalized eigenvector, so this will be x2, it will be 1 by under root 6, 1 by under root 6, and this will be the twice, so that is minus root 2 by 3. Sorry, yeah, this will be minus 2 by under root 3. So this will be your second eigenvector. So for, you can see, for lambda is equal to 0, these two eigenvectors are corresponds to lambda equal to 0, but the both are linearly independent. So even if lambda are degenerate, they corresponds to linearly independent eigenvectors. Similarly, you can find for x3, that is corresponds to lambda is equal to 3. If you do that, you can construct the matrix P. So your P will be, your matrix P will be generally nothing, that is the column of x1, this will be your x2, and this will be your x3. Then you have to find the P inverse, and at last you will find dA, that will be 0, 0, 3. Is this order important? Yes, this is important, because the first element will be lambda 1, because you have put x1 first, that is corresponds to lambda is equal to 0. This corresponds to lambda is equal to 0, and this corresponds to lambda is equal to 3. So this will be lambda 1, this will be your lambda 2, and this will be your lambda 3. So this was the exceptional case where you have, where the eigenvalues, not exceptional case where the eigenvalues are degenerate, but still you can find the eigenvectors as linearly independent. So you have to check about the linearly independence of the eigenvectors. So let's move further. So there is an important comment about the matrix that we are dealing about. We have not taught what type of matrix that P is. So for diagonalization of a matrix, we have written that is equal to P inverse of A times P. So one can ask a question, what is nature of P? What is the nature of this matrix P? So if you have P, you have P inverse. If you check the nature, so that will come out to be unitary in nature. So P is a unitary matrix if it is in a complex plane, or if there is a complex eigenvector, so it will be a unitary. If you have a real, then it will be a your orthogonal matrix. Okay, so these were the things about the P matrices. So P is unitary in nature. So in case of similarity transformation, matrix P is always unitary in nature. So this is a kind of similarity transformation. So till now we have seen where the linearly where there was a linear dependence of eigenvalues, and we find that eigenvectors are degenerate. Sorry, eigenvectors are linearly independent. Let's move to one more example. So I am doing it very quickly. Let's say a matrix C, that is your 2 1 minus 1 4, and this is your exercise. To work upon this, you will find that eigenvalues are 3 3. So if eigenvalues are 3 comma 3, so this is linearly, sorry, why I'm writing again linearly and this, I'm really sorry. So you can say that these are degenerate case. So for degenerate case, you have to check the linear dependence or independence of the eigenvectors. So let's call the eigenvectors to be x, that is x1, x2. So from the characteristic equation, you will get 2 minus lambda 1 minus 1 4 minus lambda times x1 x2 is equal to 0 0. This is a basic eigenvectors, how to find the eigenvectors. So you can come to the conclusion. So your lambda is equal to 3. So this will be a 1, sorry, minus 1 minus 1 1 1. This will be x1 x2 is equal to 0 0. So this implies that x1 is equal to x2. Okay, so for this you cannot transform two eigenvectors, because if you put x1 is equal to 1, your x2 will be 1. So if you are writing in normalized form, then x, your normalized eigenvector, will be equal to 1 by under root 2 1 by under root 2. So there is only one eigenvectors, and okay, so this matrix C can't be, this matrix C can't be diagonalized. So this was about the diagonalization of a matrix. So now I think we should do some more problems and see the interesting results from them. So let's move to one such problem, and the question is here this. Okay, so your A and B can be diagonalized simultaneously, means there is a matrix A, matrix B. Diagonalized simultaneously means that can be diagonalized by same matrix, that is P. So which of the following option is correct, or we have to comment about the matrices or which the properties they follow. So I suggest you to do this. If not, then see this. So let's move on to solution. If they can be diagonalized simultaneously by same matrix P, so we have a matrix, that is P, which can do, sorry, we have a matrix P, this can do these types of transformation, that is it can diagonalize dA, the in P inverse AP, and it can at the same time it can diagonalize dB, that is P inverse of BP. So dA and dB are the diagonal matrices. Okay, so if dA and dB are the diagonal matrices, so you know dA and dB are diagonal form, in the diagonal form. So you can always write dA dB is equal to dB dA. Okay, so from here let's put it as it is. So P inverse AP, this will be P inverse BP, this is P inverse BP, P inverse AP. You know the order of the matrices are very important. So this is P inverse AP, P inverse BP, this is P inverse BP, P inverse AP. So this P and P inverse becomes identity, because P is a unitary matrix. So P inverse becomes identity. This will always also becomes identity. So this will transform to P inverse AB P is equal to P inverse B, sorry, P inverse BAP. Then multiply the matrix P from the right hand side. Then you will get P inverse ABP and P inverse from the left hand side. So we'll get P inverse is equal to P inverse BAP P inverse. So this will again become identity, this will become identity, this will become identity. So this is AB is equal to BP, sorry, AB is equal to BA. This is nothing but the commutation of A comma B is equal to 0. So let me move a little bit down. So this become A commutation of A comma B, that is equal to So 0. So this is the correct option, that AB is equal to B, AB is equal to BA. So from this example, it is very clear that if two matrices A and B commute with each other, then they can be diagonalized simultaneously, or they have a common eigenvector. So from here, this is an important note which you all can write here, that if two matrices A and B commutes with each other, then then they have common eigenvector, CO, common eigenvector. And if they have a common eigenvector, they can be diagonalized simultaneously. Okay, so that was the thing. So please correct the spelling of diagonalized. So this was the important note, and this you will use this is a very important thing when you will study your quantum mechanics. So this is the most important. There is one, this basically this is a theorem which says if two matrices A and B commutes with each other, then they have a common eigenvector, and I proved it by doing an example that was just above, in which A and B commutes with each other, and the question was they can be diagonalized simultaneously. So yeah, I formed just a reverse problem of this theorem. So you will use many times this in quantum mechanics, wherever you will be dealing with matrices and linear vector spaces. Everywhere you have to uh, very clear about this theorem, that if two matrices A and B commutes with each other, then they have a common eigenvector and they can be diagonalized simultaneously. Okay, so let's move further. So till now we have studied about the diagonalization of a matrix. So now we will move further. So before going further, I would like to ask some questions, that if I have a matrix A, okay, now I wish to find what is A raised to power m, what is E raised to power A, what is sine of that matrix A, what is cosine of this matrix A, what I am also interested on log function of A. And remember, these A is not a number, okay, these A are matrices. So how to find the function of a matrix? So this was the problem. So I would emphasize on you this problem where you have to find the, this is also a matrix A, okay, this is also matrix. So A is the matrix power m, exponential power of matrix, sine of a matrix, cosine of a matrix, logarithm of a matrix. So obviously these all be the matrix. So the next task is how to find them. If you have, let's say I given a 3 cross 3 or 2 cross 2 matrix, and I say you to find the sine of that matrix, or the exponential of the matrix, or the let's say 1025 power of that matrix. So how would you calculate it? Or the exponential of the matrix? And this is the most important topic. So I would, so this is the most important topic everywhere, like in TFR 2000 sorry 18, if TFR 2018, JNU 2018 exam, and just 2018 exam, every exam has a common question from this topic. So this is the most important topic for all the entrance exams, first. And the second thing, in many of the times when you will be dealing in quantum mechanics, when you will study later in your master's course, then you will realize you have to deal with the exponential of a matrix very times, or the sine or cosine of the matrices. So it is important to know here very clearly and rigorously on how to do that. Okay, so I'm emphasizing, please do take a proper attention on this topic. It's going to be important. So I'm just giving you the brief idea how you can calculate it. So let's just do this problem. So if I have a diagonal matrix, so suppose I have a diagonal matrix that is just D. Let's call these elements as A, B and C. It's 0 0 0 0 0 0. Okay, now I'm interested in D square. Then you have to multiply this matrix D with this matrix D because it is diagonal. So you will get A square 0 0 0, B square 0 0 0, C square. In the same way, if I ask what is the D raised to power M, then you can simply conclude it's A raised to power M 0 0 0, B raised to power M 0 0 0, C raised to power M. Okay, so this is a special matrix where there is just a diagonal form. So let's study first the diagonal form. So this is the first topic, first form of the matrix where D raised to power M has to be found out. If I say find E raised to power D, so okay, let's realize this by an operator form. So let's draw a line here. Okay, so if I say that e raised to power x, if I say x is a number, what will be that? It will be 1 plus x square by 2 factorial plus x cube by 3 factorial plus x4 by 4 factorial and so on. So these x are numbers. If so, the expansion of exponential will remain the same if e raised to power a, where a is a matrix, then you can write this as identity, where I is replaced by identity, a is replaced by a, this is plus a square by 2 factorial, where a square is a times a, plus a cube by 3 factorial plus and so on, where a cube is defined as a dot a dot a. Okay, 3 times you have to multiply. So these all is a matrix. So this exponential is e raised to power a whole becomes a matrix. Okay, so that was the basic idea of the exponential. So if I do this type of calculation for my exponential of this above matrix, what will I get? Let's do it. So if I say find e raised to power d, so you will get 1 0 0 1 0 0 0 0 1 for this, plus the matrix d plus the matrix d square by 2 factorial plus the matrix d cube by 3 factorial and so on. So I just resolve the identity. So you will get 1 plus the first term of this matrix will be a, plus from here you will get a square by 2 factorial and so on, and this will be 0 0 0 1 plus b square by 2 factorial plus and so on 0, and this is 0 0 1 plus c square by 2 factorial plus so on. So you are basically left with exponential of a 0 0 plus 0, exponential of b, exponential of c 0 0 0. So your exponential is d, but nothing the exponential of the components of that matrix. Similarly, you can expand the sine and cosine functions. So you can write your sine of d is nothing but sine of a, that is a matrix 0 0 0, sine of b 0 0 0, sine of c. So this is basically the sine transformation. If I say you the cosine transformation, cosine of d, so it will equal to cos of a 0 0 0, cos of b 0 0 0, cos of c. Okay, now again if I say the log function ln d, where let's make a convention clear, this log has a base 10 and this ln is also for base e, base of e. Okay, so this is also log function, so this will be ln of a 0 0 0 ln of b 0 0 0 ln of c. Okay, ln of c. So now you can find the all functions of a diagonal matrix. So you can find diagonal raise, if d is a diagonal, if d is your diagonal matrix, then you can find these functions: d raised to power m, e raised to power d, cosine d or sine d. You can find out, you can find out the log of d. Any functions you can now find it out. Now our original matrix was A, which is not a diagonal matrix. So how to find that? So let's let's use the concept of diagonalization and do this problem. So the idea is very simple. So what is the idea here? You know that your dA is equal to P inverse of AP. Okay, and you have to find a raised to power, let's say, m. Then how to do it? And you know, you can find out d raised to power m. Okay, so what the idea is very simple. So you have to find out this a raised to power m. You know d raised to power is the all the diagonal power m of that matrix. So let's write d a raised to power m. So this is equal to P inverse AP 1 times, P inverse AP 2 times, P inverse AP 3 times, and in such a n times P inverse AP. So recall the property of M. This is a unitary. This is unitary. This always be unitary. So you get this. So it will be P inverse A. How many A's will be there? A, M times. This is P. Okay. So there will be M A's. So this is equal to P inverse A raised to power M P. So this is nothing but BA power M. Now you can multiply this by P. So your original function was this P inverse A raised to power M P is equal to dA raised to power M. Now you can multiply by this P inverse from left, so from right, from left side, and P from right side. Let me make it correct. So you can multiply P from left and you can multiply P inverse from right hand side. So you will get this equation. So this will be again identity, this will again identity. Then you are left with A raised to power M is equal to P dA raised to power M P inverse. So you know it is a very complicated process. It is, but that is the only way. So if you have to find the matrix power M, first find its diagonal form, do the exponential, the diagonal elements that are your eigenvalues. Let's say it was ABC, then the diagonal elements of dA power M will be A raised to power M, B raised to power M, C raised to power M, then multiply by these matrices P, then you will get A raised to power M. So let's just write the quick forms of this equation. So I just do for one, so you can similarly do for all. So A raised to power M will be P dA की power M P inverse, and you know what dA power M is. Exponential of power A is equal to P exponential of dA P inverse. Let's move to sine of A is nothing but P sine of dA P inverse. Cosine of A P cos of dA P inverse, and log of A will be basically, you all have written already, that is ln of dA P inverse. Okay, and you know all what these matrices are: dA power M, E raised to power M, this and this and this. So you know all these things. Okay, so That was the thing, and it was a very important and very uh, important topic for you to understand, because it is important as well as it is necessary for all the exams. So why don't we do a problem on this, based on this problem, so it will be more clear you for that. I am knowing it is going to be a long lecture. It is already 45 minutes and 27 seconds. So let's do one problem. So, and this problem was asked in just examination, that is in 2016, so you can get problem from here. The question was, your matrix M is given to be 2 1 1 2, and you have to find out what this is, that is cos of pi m by 6. Okay, so you have to find out this. So I'm not going to do it whole problem, but I will just hint you how to do that. If you find the eigenvalues, then eigenvalues 1b1 comma 3, just find out the eigenvalues. Okay, and for corresponding, the diagonal matrix will be, let's call this 3 0 0 1. It will be the diagonal matrix. So if you put, then this pi by 6 will be pi by 6 dm, pi by 6 dm. If I wish to find, then it will be pi by 2 0 0 pi by 6. Okay, we have find out this pi by 2 0 0 pi by 6. Okay, then we have to find out this quantity, that is nothing but cos pi m by 6. So it will equal to p cos dm, and this times p inverse. Okay, now we got this, we have this, we have this, and sorry, this will not equal to this. There is one slight correction in this term. So this will be pi by 6 times dm, because this has to be the same function. So this is p inverse. Now your task is to find the p inverse, that is the p and p inverse. So it is going to be hectic for you to do it, but I did it and I found that p is equal to 1 by under root 2, 1 by under root 2, minus 1 by under root 2, and 1 by under root 2, and your p inverse is 1 by under root 2, 1 by under root 2, minus 1 by under root 2, and 1 by under root 2. So please do these calculations and find the p and p inverse, and it will be also for you to practice for this problem. So if you do this, you will just multiply by these matrix by this matrix, so you will get cos pi m by 6, that is nothing but under root 3 by 4, and that is 1 minus 1 minus 1 1. Okay, so these options were given, but I have not given you the options, so this will be the answer, root 3 by 4, 1 minus 1 minus 1 1. So this was the problem that was asked in just 2016 for the same topic which I have discussed with you. So I encourage you to do more problems on it. Find the previous year question paper or books or any other material wherever you can find the problems on these books, and just do a practice. And if you do the practice, you will be having like directly finding the dm by just knowing its eigenvalues and do the sine cosine functions, and you will be able to do it more quickly. So this was all about the diagonalization of matrix. In the next lecture, we are going to study about the rotation matrix for coordinate transformation, that is by rotation, basically the coordinate transformation by rotation. So that is also going to a very important topic, because it is very much of, look, it appears too much in like in tensor mechanics, in rotations, in quantum mechanics, everywhere. So you have to be pay attention on that also. So till now, for diagonalization, that is enough for today and for your JAM and JUST and TFR examinations. So if you have not subscribed the channel, do subscribe the channel for other latest updates, and your suggestions and comments are always welcome. So thank you. Meet you next time.